So for the last, today's Thursday, so the last 3 days, I've been trying to convince you and trying to indoctrinate you to believe me when I say that if Ben comes up here and stands on ice skates, and I come up here and stand on ice skates, and the music starts, and we have somehow become amazing ice skaters, right? Do you ice skate? Do you ice skate? No, like literally, this is what happened. We'd push and we'd fall. It'd be amazing. Yeah, probably not worth winning a gold medal though. Anyway, so we're gonna stand there and we're gonna push. And I've been trying for the last few days to convince you that Ben's gonna push on me, right? And what do I do to him? Same thing. And how do the forces compare? They're equal, right? Yeah. We've been saying it over and over and over. We have never actually shown that it's really true. Has that bothered anybody? Yeah. One person was willing to admit it. Somebody were like, I just take your word for it, Ms. Carbling. You seem pretty trustworthy. I understand that I try and put on an air of trustworthiness. But for those of you that have had a little skepticism at some point in the last 4 days, today is your day. Are you excited? Josie, you don't look excited yet.
Oh, I just don't care if I know. Like, I know.
You just trust me. We just have like an air of trust. You're just like, yeah, it's got to be true.
Yeah.
Okay. So for those of you for whom I don't seem as trustworthy, I guess this is who this is for. But we're going to do it anyway. What is Newton's third law? Newton's third and, oh, by the way, most important law. What does it say? We wrote it down yesterday. We've been talking about it for a few days. What does Newton's third law say? I don't know. I do.
Bad way or the good way?
Not the bad way. The bad way means you like that. It means nothing. What is the good way to say Newton's third law? Yeah.
Is it like for every action?
Ah!
I wasn't going to say I was just going to say action.
Oh, but yeah, but I want to say action because action means nothing. What does that mean? So let's.
For every force, there's like equal or opposite force.
At the same time.
At the same time, the same amount of time,
Yeah.
They're exactly the same. Yes. Yeah. You're living in a space that's kind of cute because I don't live in that spot. Like I just want to get rid of those words because they confuse me. But I understand that you're trying to meld these two. You've got your science teachers from all of the rest of your existence versus me, right? And I'm trying to convince you of something different. Isaac still doesn't trust me or believe me at all, which I think is awesome.
Like
So, what's that?
I like this one.
Oh, okay. So Ben says for every force, there also exists another force, right? I'm changing your words a little bit, but is that okay?
Yeah.
So for every force, there exists another force. Because can you have a force by itself? Not possible. For every force, there exists another force. They act on opposite objects. That's important. They act in opposite directions for the same amount of time, and I'm claiming that they're the same size. So that's really what we're talking about. That is Newton's third law. The hardest part of that claim to convince students of, by students I mean all y'all, is this part right here. Is that the force of A on B is the same as the force of B on A. The time thing makes sense, right? Once you've let go, you've let go. And once you've pushed, like that stuff makes sense. But the size is the thing that I think often is sticky for people. So that's the claim that I want to address today. So here we go. So I'm going to say that my claim is that the force of A on B is equal to the force of B on A. Okay? And today we're going to look at some videos and we're going to do some analysis to see if this is really true. Okay? There are 2 videos that we're going to watch and one that we're actually going to do the analysis for. And I'm going to pull up one of them just so you can take a look at it and you can kind of get a sense of what we're really talking about. Oh, maybe it's going to go. Oh, dear. Okay, so we've got these two ice dancer types, right? That are pushing apart. So this is really what we've been talking about for the last 2 days. It's just another thing. We're gonna watch it one more time. So at that moment, right before they start, what's their velocity? 0. Person 1 is gonna push off from person 2. Person 2 is gonna push off of person 1. And they're gonna start moving. They're applying a force, 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 no more force, right? So during that time when they were applying a force, what was happening to their velocity? It was going up, up, up. They were speeding up, right? Now that they are no longer in contact, remembering that Star Wars is just a movie, okay, are they applying a force to each other now? No, there's no more force acting between them, okay? And so now tell me about their velocities as they travel. Well, if we assume that, we're going to assume that the friction is very, very small, right? That's why they're on those little skateboard type things. So it should be constant, right? Yeah, yeah. And they tell us what their masses are too, Haley's mass and Connor's mass, so we've got a sense. Okay, so we've got another video like that we're going to do the analysis for. I just wanted to show you kind of one at a time. All right. So my claim is that the force of Haley on Connor is the same as the force of Connor on Haley. I'm just going to call them A and B because I already have it written that way. Is there a way in that video to measure force? Do I have a force meter that I had in that video that I can see how hard somebody's pulling or pushing? I don't, do I? No. So we need to break this up a little bit. So we're going to do a little bit of thinking here before we actually do the analysis. So I know from Newton's first and second law that the acceleration of an object is equal to the force on that object over the mass of that object. Is that an okay statement? You guys okay with that? Newton's first and second law, we've kind of decided that that's a true statement. So from that, I can say that the force of B on A is equal to the acceleration of A times the mass of A. How do you feel about that? So my claim is that that thing is equal to the force of A on B, which is really the acceleration of B times the mass of B. Are we okay there? Okay, I don't think I did anything too scary here. And the only reason I'm doing this is because I don't know how to measure force from that video. I don't have any force meters. Do I have any accelerometers that you saw in that video? Accelerometer would be a meter to measure acceleration. Should we watch it one more time? Do you remember what it looked like? Watch it again. Play again. All I can see are the two people's motion, and I do know the masses of them, so that's helpful. Yeah. So I don't know the acceleration, but what's acceleration equal to? Anybody remember the other thing that acceleration is equal to? Do you remember?
Changing velocity over time.
Yeah. Like final velocity minus initial velocity. Is it okay if I write it like that? Divided by time. So I'm just really trying to get from something that I'm claiming. I've been trying to convince you of this for 4 days, 3.5 days, I suppose. Okay, to something that I can actually measure because that's much more helpful. So instead of, I can't find acceleration, but I can find velocity, can't I? Because I know that velocity is distance over time, right? That's helpful. That's helpful to know. So I can find the velocity. So let's write this down. So I'm going to say the final velocity minus, hi. That was just me. Initial velocity over time for A times the mass of A, I'm hoping is equal to, Isaac is not convinced it's true yet, but we'll see. The final velocity minus initial velocity for B divided by time times the mass of B. Is that okay? I'm just trying to get someplace that I can measure stuff. What's the initial velocity for each of those people? What do they start out at? 0. Let's get rid of it. Make our life better, right? How do the times compare? The times that the forces are applied? They're the same, right? I can't push more than you can put, like, for a longer time. So I could multiply by t on both sides. Those really go away. Are you guys with me? Is that okay? If I got time on both sides, those are going to go away. So really, I've got my claim now is that the final velocity for person A times the mass of person A, my claim is that that may be equal to the final velocity for person B times the mass of person B. Are those things that I can measure from the video? Yeah. I mean, they tell me the masses. I can measure the velocities. So before I move on, I want to make sure that you are convinced that if I can prove that this is true, then you know that this one is also true. How do you feel about that? I don't want you to think there's any funny business. Yeah.
Wait, so the time part, I mean, I know it's math when you like multiply and then you multiply on the side, they both cancel. But
Yep.
why are they the same in that part?
But why? That's a good question.
Because
So
one's gonna hit the tick mark, that 15 centimeter tick mark before the other one because of acceleration. So is that time different than the other one?
well, let's figure out where the time comes from. What time are we talking about? So we're talking about, that's a really good question. We're talking about the time for the acceleration.
Okay.
How long does each of them get to accelerate? Is that okay?
Yeah.
And the time that it gets to accelerate is only the time when there's that force being applied.
Okay.
The other time, like the time for the distance, those will be different because they're traveling at different speeds, perhaps.
Yeah.
Is that okay?
Yeah.
Okay, cool. So, we good? All right. So we're going to take a pause for a moment. I need you to get your computers out. We're going to do a two-step process. I'm going to teach you how to measure velocities with a simple video first, okay? And then I'll let you figure this one out, okay? So you guys get your computers out. If you need to plug in, go ahead and do that, whatever needs to happen. And then we will regroup to do our other stuff.